Here I am, Ishan Chattopadhyaya from LucidWorks. I'll be talking about an OpenStreetMap geocoder based on Solr and Lucene. So, I also belong to the OpenStreetMap Foundation, where OpenStreetMap is a mapping website similar to, let's say, Google Maps, Bing Maps, or a geographical information system. The beauty about OpenStreetMap is that the data is open, everybody can contribute, and the data belongs to everybody. It's not held by some corporations. So, in essence, you can say OpenStreetMap is a Wikipedia of geodata, where anybody can collaboratively edit the map. The benefits of having this platform for everybody is everybody can map their own localities irrespective of whether a commercial body is interested in your area or not. So, for example, if you want to map all the trees, all the rubbish bins, or what have you, onto a community map, you can go to OpenStreetMap and not worry about any licensing issues. The data stays with you. So pretty much like Wikipedia, you of course have some relevancy guidelines. You must not put in junk, otherwise community members can edit and probably clean up all your junk that you put in. So OpenStreetMap is a project aimed squarely at creating and providing free geographical data such as street maps to anybody who wants them. And anybody is a pretty loose term, where this means that anybody can use them for whatever purposes they want. Commercial, be it non-commercial, do whatever you want. So, just to give you an appreciation of what OpenStreetMap, actually, how many of you have actively used OpenStreetMap at one time or the other before? Okay, so I think we have two of us. So I'll probably then get into this and show you a comparison as to how rich the data is. So here's an example. I think this is somewhere in Berlin. On the top left, we have OpenStreetMap. On the top right, we have Google Map, and bottom left is Bing Map. So to give you an appreciation of how much data people have actually volunteered and put in some places, probably like Berlin, this probably surpasses the level of details that the maps have against all other commercial entities like Google Map. Actually, in Europe and specifically in Berlin or in areas in Germany, Google Map is probably inferior in terms of details as compared to OpenStreetMap, which is a big win. But the state of OpenStreetMap, of course, is reliant upon the fact that people need to volunteer. And in various places where IT is not as prevalent among masses, probably in many places in Asia, many places in Africa, even the Americas, there the state of map is not as competent against some of the commercial entities, but then it's catching up fast. Focusing our discussion only on Europe, it's pretty good, pretty damn good. So here in this demo, we probably see Bing Map has pretty much absent details. Google does fine, but OpenStreetMap really rocks. So to come to how OpenStreetMap is built, I'll not get into too much details into this, how OpenStreetMap, the stack and the architecture of the backend infrastructure works like. Important parts of this are that there's an indexer, there's a map renderer, there are various other exporters, transformers. One of the important parts of this entire infrastructure is the geocoder, which is what I'll probably be talking about here in this talk. So what is a geocoder? If we look at a geocoder, it's tightly coupled with the search on a map. So when a user comes into a map service, types in whatever locations they want to search for, whatever places of interest they want to look for, the job of the geocoder is to accept a raw query in the natural language, probably unstructured, but not to a lot. Not to a very crazy degree. A query can be like hotels near Dublin, hotels inside Dublin. It could be Dublin itself. It could be Berlin, Germany. So various queries. Hotels is one of the popular queries people type in. Other examples would be just a place of interest itself, like probably the Weaver Stadium or the Clyde Court Hotel. So the job of a geocoder is to take in that query and give out some lat-longs, the latitude and the longitude, the geocoordinates. So it can be based on basically two different kinds of search. One would be a search for cities or places, towns. The other could be search for so for example, a search could be just Dublin. So basically these are administrative areas, Dublin or the state where the county, Dublin County, or United Kingdom or Republic of Ireland. So these could be places only searches. And then there could be some points of interest or business listings based searches where we could have more of a partial text match kind of a search. So for example, the Clyde Court Hotel could be as well be searchable by the user query Clyde Hotel. So basically, first of all, one mode of the geocoder would be to search for only places where the user query contains the place name, and you have probably, and most, if it's unambiguous enough, you'll have one set of geocoordinates for that place. On the other hand, if it could be a search, for example, a hotels near Dublin, it could be a list of geocoordinates. But the output, of course, is geocoordinates. So to give you an appreciation of geocoordinates is the latitude and the longitude of a place. So that's on an Earth, every place has a defined latitude and longitude. So what is Nomainatim? OpenStreetMap, the website, I'll probably give you a brief look at how it looks like. So there you have OpenStreetMap. You can probably search for Republic of Ireland. You have lots of results. And the geocoder powering these searches is, as you see, Nomainatim, OpenStreetMap Nomainatim. You could do other searches like Dublin. There are hotels in Dublin. So you get all kinds of results from a geocoder. So Nomainatim is the OpenStreetMap's official backend geocoder. It's written in PostgresQL and PostGis. It's basically powered of a RDBMS kind of a infrastructure. So the goal of my talk and the goal of the prototype that I'm probably going to present to you, this is a use case for how we can use Solr to build the a similar geocoder with better capabilities than probably what was originally programmed for in the PostGis based geocoder. So again, just to reiterate what we are looking at, the goal of the geocoder is to search for, of course, cities and towns, streets, address points, places of interest. The other problem which generally a reverse geocoder solves, which is not really a geocoding use case, but it's a reverse geocoding use case, where given a lat long or given a geocoordinate, figure out which place is it belonging to. So I'm here, this is my geocoordinates. Where am I? What is the geotag? What is the name of the place? So that's geocoding. And so one of the important goals of this project would be to have fuzzy queries, support for fuzzy queries. So when we say fuzzy queries, I generally mean better support for international queries, better support for stemming, better support for phonetic matches, better support for spell check, some of which are there in Nomainatim, but most of it is not there, probably because of difficulties with the current code base and the infrastructure that it is powered off. And Lucene and Solr being very well suited to support spell check, so this presents itself as a natural use case. So how did we come to this? Why did we not build a geocoder like Nomainatim right up front? Well, there were a couple of things which recent changes in Solr and Lucene have brought in, which has made this possible. The most important things are the spatial support, the improved spatial support, thanks to David Smiley and others who have worked on it. And for reference, David Smiley's Lucene Revolution talk earlier this year is linked. The kind of spatial capabilities that have been brought into Solr were only previously known to have been present in PostGIS or more traditional GIS systems. There have been other GIS systems commercially available, like ArcGIS, and those systems have been really the state of the art in terms of spatial search, spatial processing, spatial filtering. But thanks to David Smiley and his work, very good features are now available in Solr. The spatial predicates like, so initially Solr could only index a point shape as a geocoordinate for a document. It was not possible for a document to have a complex geometric shape. So for example, it could be a polygon, it could be a polystring. So it was not very easy to index and search on them. For example, a street or a city which has a defined boundary, or do other crazy stuff with such stuff. So thanks to these features, this is there. The other benefit is the SolrCloud mode, where you can have a distributed index. And of course, I guess we all have used SolrCloud. Earlier, although this was not a technical limitation, but it was very difficult to build a geocoder which could have scaled horizontally as the data grew, or it was difficult to partition the data into various geographical regions or whatever requirements that the geocoder may have had to. And probably this is the reason why Nomainatim is powered of a single server, a big fat server sitting on a 64 GB machine and probably serving very well till now, very fast. But there's probably only so much to it in terms of scaling up. You can probably only vertically scale it up. Thanks to SolrCloud, this is possible here. So the architecture of this would be pretty simple. There's an indexer, which is basically an indexing pipeline. The raw OpenStreetMap data comes in through the indexer, goes into a Solr instance, and is served off API layer and served into a front end. Front end for this is not ready yet, but there's a website as a placeholder. So to understand what is it that's going into the Solr index by way of the indexer, and how is it that the OpenStreetMap data is organized, we have to understand three basic constructs, three basic elements that make up the data: a node, a way, and a relation. A node defines a single geospatial point, a latitude and a longitude. So a node can be a single point in a map. For example, if it's a hotel with no defined boundaries, you can have it as a point marked there. It could be a street intersection. It could be just about anything which is just a single point. A way is more like a polyline, a collection of nodes, and a way is used for streets. A way is used for even having polygons, which are self-joined polygons. Self-joined way is a polygon, and a relation, where a relation is relation joins many ways and nodes together to form a single geographic administrative entity. So, for example, if it's a country, let's say it's Republic of Ireland, it could be made up of many polygons, many ways, many nodes along the way. So it's just a logical grouping of all the ways to represent them as single entity, let's say Republic of Ireland, or maybe County of Dublin. So before we proceed further, I'd like to bring about an appreciation as to some of the difficulties that are faced while doing this work or while doing any kind of data processing on the OpenStreetMap data. So while OpenStreetMap is pretty much a free-for-all kind of a editing interface for all the users, there tend to be some users who are more diligent than others. So, for example, if had it been the Viva Stadium, one user might be very diligent looking at the satellite picture and actually plotting Aviva Stadium's entire boundary and calling it as a point of interest and naming it as Aviva Stadium and adding more metadata. Some of the more new OpenStreetMap contributors may as well just represent it with a point which represents Aviva Stadium, probably the center of Aviva Stadium. And after that, they could as well put in some metadata if they are grateful enough. And there lies the problem as to lack of enough metadata to do these indexing. The other problem would be if a mapper is not very careful enough, they could break polygons, which have probably been already indexed. By this, what I mean is a polygon is a way whose starting point and the end point are the same. So, in general, say it's a country like Republic of Ireland, it should be a polygon which is complete. It is possible to break some nodes in between and break the polygon, and there are validation methods, but sometimes they don't work, and hence it might be difficult to index such data. So some input validation will be required for this. Just to give you a brief idea of the scale of the data that we are talking about, the entire OpenStreetMap across the world has around, well, how many? 2 billion nodes probably. 2 billion nodes, 202 million ways. So pretty big data if talk about indexing it. So now we come on to the schema of the infrastructure that we are trying to build, the project that we are trying to build. So ideally, we would want to index the entire data into a simple index with the schema which has administrative areas 1 through 7, defining all the administrative areas that may cover the geographies. Administrative area 2, admin 2, usually stands for the country that every record belongs to. Administrative areas 3 to 7 are pretty much left to each country's internal hierarchy of geographies. So, for example, admin 3 could be a province in one country, or it could be a county in another country, or generally what happens is administrative area 6 has the city or the metropolitan area. Administrative 7 has subdivision of a city, and 2 to 6 are somewhere in between. It could be a province, it could be a county, as and when the communities of the countries decide they propose how it should be timed. For example, in Ireland, this document holds true. Admin 2 is Ireland, admin 5 is Dublin County, admin 6 is the city, the metropolitan area. And Ballsbridge is a suburb or a locality or a neighborhood, as in the US. So the idea of having this indexing schema would be to normalize denormalize each of these documents so that searching can be just a multi-field query into these documents. How we index this data into this is slightly tricky. So I'll just briefly touch upon it. First of all, we gather all the polygons that we have for a country. Then we gather them and index them. Then we figure out all the polygons. So the country polygons will be indexed in admin 2. There will be a document for admin 2. So all the other documents now will have either state, city, street, or something or the other. Now we pick up the documents which have admin 3 in them. And now to make an association for that admin 3. So let's take an example, maybe Dublin County. We have a record for Dublin County, which in the OpenStreetMap is just a way. How we associate that with admin 2 would be by doing a spatial containment within Solr. So unfortunately, the mappers may or may not associate enough metadata with the document itself, with the way itself, so as to associate it with the country that it belongs to. So the only foolproof way of doing it would be spatial containment. And that's what even Nomainatim does, and that's probably what we have to live with. And hence, the indexing is a rather slow and painful process where you have to go along validating the data that you're containing within. And this indexing schema finally is the holy grail where we reach to. Another indexing schema for the places of interest is similar, where so this is another document. This is probably a previous one was a street document. The other one is a city document. So this one is a schema. It's a different index for the points of interest. The points of interest will have a name, a category, a shape, and all the relevant administrative information. So how do we search? So now we come to the interesting part. How do we search? So first of all, a query comes in, a raw query comes in into the classifier. So this component is in the entire system above the base index, above the Lucene index. So before we hit, so it's an in-memory classifier where a query comes in. So maybe the query could be hotels near Dublin. The query comes in. The classifier identifies or annotates parts of the query as possibilities, which part could mean which geographical entity. And then a validator then validates all these classifications, and the geocoder actually does the lookup. The geocoder is nothing else but the Lucene index or the Solr index in this case. So how does classification work here? So the raw query comes in. Actually, some of the labels on these arrows are not showing up for some unforeseen reason. The query comes in, then the tokenizer tokenizes them into shingles. The shingles then pass through what is known as a Bloom filter. So I'm sure you must know about a Bloom filter. A Bloom filter is nothing but a very efficient data structure for doing set memberships. So you insert many items into a Bloom filter. Then you want to check against the Bloom filter whether a given item is inserted inside the Bloom filter or not. The Bloom filter will, in a probabilistic manner, tell you with a high degree of probability whether that document is inside that or whether the term is inside the Bloom filter or not. If it is there, then it's 100% probability it will return, but it can also return false negatives. Benefit of Bloom filter as compared to any other similar data structure like a in-memory hash set or in-memory tree set or something would be that a Bloom filter consumes very less memory, and a Bloom filter is always faster than other data structures. So here we take an example, and I'll try to run you through how the Bloom filter works. So given a query, hotels near Lansdowne Road, Dublin, which is the road on the street on which we are currently in the Aviva Stadium. So given this query, first of all, the shingles are generated based on this query, the tokens. And there are one-word shingles, there are two-word shingles, there are n-gram shingles, right up to the length of the query. So before I proceed, are there any questions leading up to this? Or are we good to go? Okay. So now how this classification layer, so I'm talking about the classifier now. So how this classification is working for the Bloom filters is, we initially, when the index loads up, we create some in-memory Bloom filters, as I said, these cylindrical boxes, these cylinders on the bottom of the slide, for each of the fields that are there in the index. So category is one of the fields in the places of interest field, the administrative area 2 through 5, streets. So given each shingle, we try to pass them through the Bloom filter to understand which of the possible fields it could belong to. The Bloom filters are populated at the beginning using the term query component of Solr. So given Dublin, probably it will pass through the administrative area 5, which is the county probably here in this case. Streets will pass because there could be a Dublin road somewhere in probably Limerick or somewhere else. I don't know. Similarly, Lansdowne, it could be there is a city by the name of Lansdowne somewhere, and Lansdowne is also a street in Dublin. So both the Bloom filters give you a positive match there. So given this query, and after the classification layer, we have certain classifications, like the hotels keyword is a category, could be a category. Lansdowne is an administrative area 5, and so on. Now the next step, so this is, till now we have done it very fast, probably in a matter of few milliseconds. The next step would be actually to validate whether all these assumptions hold true, or which of these actually make the most sense. So there we go for the possibilities of the various combinations of these classifications that we are led to. This is a combinatorial problem. Some of the possible permutations are that, so in the possible permutations, it's C.5.5, where dot is indicated by an unknown geography. So in this case, C.5.5 possibly means the first term is a C, which is a category. The second term is unknown. The third term is administrative area 5. The fourth is not known, which is the RD, the road is not known. And Dublin is a city. And there's the second permutation, which is which says hotels is a category, Lansdowne is a street, and Dublin is a city, which is probably the one that we are looking into, we are interested in. And there could be other possibilities. So the idea is, once we have established a containment relationship, whereby we want to establish the fact that Lansdowne Road is contained within Dublin, and hence it's part of this query. The location of this query is Lansdowne, Dublin, and the search term is hotels. So once we identify what the location is, what the search term is, we can go around figuring out the geocode for the location and do a spatial search for that search term near that location using a spatial search. So in this case, we try to see what are the different permutations which are valid. The way to do this, what we are looking at is a Solr query, a Boolean query where we pass all of these permutations into the Solr index to ascertain whether there exists even a single document for some of these user queries, these Boolean queries. Some of them will have at least a document, in which case that is a valid permutation. Some of them will not have. For example, in this case, the index structure, if you remember, has a admin 5 field, which will either have Lansdowne or Dublin. One record will have either Lansdowne or Dublin. And it's not possible for the first permutation to go through because it contains both the clauses, both the Boolean clauses for Lansdowne being the city as well as Dublin being the city. And hence, this query will be invalidated. There won't be any results for this. The second one could hold a positive match. The third one should. The third one should not, and so on. So the third one did not work because in the city Lansdowne, there was no street named Dublin. And had it been there, it would have resulted in another combination to worry about and to rank. So based on this, we understand that the most probable permutation of handling this query would be street being the Dublin, street being the Lansdowne, administrative area Dublin, 5 being the Dublin, and the rest of it is probably unknown. Now what we do is, since that is the most, so there are other probable permutations. The permutation that gives us the most maximal match for the location is the second one, and hence we go for a geocode immediately. By a geocode, we mean we just go to the index and actually get the geocode. Why we didn't do it in the first pass would it be that it would have been expensive. It's very efficient to get just the counts or the number of documents that matched. Actually getting the fields out of the document would have been slower, and hence this is the second pass that we are trying it. And once we do this, once we hit the index, the geo field of the index returns a point in this case. It actually also returns a polystring, but to make the search possible, we also index a point. So why this is there is because in the current Lucene spatial contrib, the spatial module, search by a polystring is currently not possible. The search by the distance sorting by a polystring is currently not possible, line string. So we get the point where this location points to, and then the entire query boils down to, initially it was hotels near Lansdowne Dublin Road, and Lansdowne Road Dublin. Now it boils down to hotels near a spatial point, which is a simple distance search within a spatial radius of distance equal to 10 in this case. There's a filter query where the category that was identified as hotel has been brought in, and we see the results of this query, and we see all the results that we expected to. So this is how the search works and the indexing prior to this as what we discussed. Do you have any queries? Do you have any questions? Sure. Right. So, so the question is parts of the query. How do we determine whether they belong, for example, to a city or not? Right.
Yeah, because you said that before, just a few minutes ago.
Right. So, yeah. So the question is, given a part of a query, how do we identify whether it's part of a field within the index or not? Do we do an index lookup for that term? So here, as you mentioned, we want to achieve very fast results. If we look into the index and do a term query for that in the index, it is likely to be slower than what we are trying to propose here using a Bloom filter. So how Bloom filter will work here is that we take a city Bloom filter, a Bloom filter for each field in the document. City will be one of the fields. We create a Bloom filter. We add all the terms in that field into the Bloom filter, and then we do a search on the Bloom filter whether that term has been inserted once or not. So this Bloom filter is kept in memory, and the way it works is probably you'll need 10 hashes to figure out probabilistically whether all the 10 hashes are turned on or not. All the bits in the 10 hashes are turned on in the Bloom filter. Bloom filter is just a bit array. And right. Right. So a Bloom filter is created once during the startup of this service. It could be recreated again using the terms component of Solr itself. But yeah, you're right. At the start of the index, the Bloom filter is created. So there are more heuristics built into discarding these permutations, and some of them are probably worth talking about. So some of the permutations which will never occur in the real life. People may not search for, let's say, Dublin, Clyde Court Hotel, Ireland. People generally don't in terms of the user behavior. In this case, the permutation would be 5C2. 5 will be the city, Dublin occurring first. C will be somewhere in between. And right towards the end, it'll be 2, the island. This permutation probably may pass, but it doesn't have a real life chance of users finding it. Or that's not the straight case. There are many other use cases where there could be various combination of administrative areas sploon all across the query. So to defend against those possibilities, because the evaluation of each of these permutations could potentially be expensive, we already have a list of valid permutations that we should probably pass these classifications through. And you're right that the classification where C55 occurs will probably fail because this is not one of the valid permutations that we are trying to look at. So while this example is there, this will probably not even be queried. This Boolean query should not be fired. Misspellings? Yeah, that's a good question. So currently we don't. And the idea of how can we deal with misspellings is based on the fact that Bloom filters are very fast for exact matches, but not ideal to do fuzzy queries with. In this case, one of the approaches would be to figure out on an offline basis what are the common misspellings for each of the terms within the field, and then also index them into the Bloom filter. And once, let's say a misspelling of Dublin, let's say Dumlin. Somebody types in Dumlin, and we know that Dumlin is a very popular misspelling of Dublin. What we can do probably is index it into the Bloom filter. So Dumlin will as well figure out that it's a city. And then when we hit the query against Solr, then we, if we already know Dumlin and Dublin are synonyms of each other, then we can probably do a straight match. Or we can do also as well a fuzzy match to figure out from the index. But of course, this relies upon knowing upfront what misspellings could occur in. So the other option would be to have a very fast in-memory spell checking service which can identify each of the shingles while they are created. So right at this level, if at the shingling level itself we can figure out that Lansdowne is probably misspelled, or it has alternate spellings without an E or something. So then probably this spelling, maybe it can be an in-memory index or something very fast with. So at the shingling level itself, we can probably figure out that Lansdowne is probably something else as well. So somebody misspells Lansdowne, we can figure out that could be a misspelling. So the idea is to enable the service to do that. The way we can do this is for each of the admin area 2, admin area 3, and all the fields, The idea would be to have either a separate field dealing with the phonetic matches or dealing with the analyzed versions in various languages. The challenge there would be to identify, given a query, what is the language of the query and whether or not to look into the analyzed fields. But currently we don't do this, but this should be pretty flexible enough to support if we have analyzers written for all these languages. SoundX would come, maybe there could be a field for SoundX, maybe there could be a field for various analysis of different languages, or probably it could all be clubbed together in this field itself. It's just a ranking problem from there on. So coming to the challenges that lie ahead beyond this implementation would be the problem of dealing with the data inherently that the OpenStreetMap gives us. One of the problems is street associativity. So given a street in the OpenStreetMap corpus, usually there's a field called in city, which for Lansdowne Road, the tagger can very helpfully add a double into it, and hence we can easily associate it, but it may not be always possible. The official defined way of associating a street to a higher geography, as advocated by OpenStreetMap, would be to find the nearest city center, or the containing polygon, and the street belongs to that geography. Now, there are always problems with borderline cases where you have two different neighborhoods and there's a street right in the middle. You don't know how to associate that street where. So those are one of the challenges. That is one of the challenges that we need to address. Incomplete polygons is a problem, because if you don't complete if the polygons are not complete, it's very difficult to complete them without knowing what went wrong. And without the complete polygons, it's not possible to do a spatial containment, because spatial containment, as in Lucene or in Solr, works based on polygons, and an incomplete polygon will not be able to tell us whether a given point belongs to this polygon or not. The other problem is handling the data updates that keep happening on a real-time basis. So users all across the world keep on updating this index. One of the bottlenecks of this approach is the Bloom filter, whereas it supports very fast set containment algorithm, very fast set membership logic. Updating a Bloom filter is difficult. You can add entries to a Bloom filter, but if you delete entries from a Bloom filter, you have to recreate the Bloom filter all over again. So that's one of the challenges. And of course, data validation. When a user tags in something, you have probably some way to figure out algorithmically whether the metadata associated with the geography is correct or not. But the system will probably have to live with all these problems. The other things to keep in mind and ponder about as the system grows would be the need for distributed search. Currently, as I said, Nomainatim is based off a single server, very powerful server. Would it make sense to probably have geographical partitioning, whereby you have Africa in a separate index, in a separate shard, Asia in a separate shard, Europe in a separate shard? The problem there, of course, is given a query like you are always searching for cities in Asia. Now suddenly you come up with a query called Chicago. There is a hotel Chicago, or there is a maybe small city Chicago nearby in Asia, which will probably result in local searches within this Asian shard. But would you also like to do a global search then and get the Chicago from the North American shard? So these are things that we probably have to figure out. So that's about it. I'll probably have the code put up and all the details put up at this URL. And there's my Twitter ID, just in case. Thank you very much. Have a good day. Bye-bye.